And the important thing we have learned, or so far, by doing that is what? We learned about frequency response function. Frequency response function gave us the knowledge to find the damping ratio in a system, because we learned that maximum value of this frequency response function is approximately 1 over 2 zeta. So that way we can calculate damping ratio. Frequency response function helps us to find the maximum displacement, dynamic displacement, or for that matter, dynamic stress, and so on. We also learned as damping increases, what is the limit of this function. So all these, the frequency response functions basically went to 0, right? And we also learned, as of course damping increases, as long as this damping is not greater than 0.707, okay? Which, in that limit, Umax is always less than the corresponding static displacement. Then, in this case, Umax is amplified by this frequency response function, so and so on and so forth. So that's one thing we really learned by studying frequency response function. The second topic then we looked at was a special case of harmonically excited system, and that was rotating unbalance. In the case of rotating unbalance, okay, we derived the equation of motion, and we defined the pseudo frequency response function, and we saw that in this case, this is what we experienced, okay, that no matter what the damping ratio is in the system, the response will never go to 0. Not only that, there was a big difference between these two. Here, the peak is shifting toward the right of r equal to 1. Here, peak always shifts to the left of the right, r equal to 1, and so on. So this is what we have so far studied. And the third thing we have been studying is time-dependent this input displacement, right? So what we looked at was that if you have a system, okay, that if the foundation moves, let's say y of t, what happens to the system? Instead of having a forcing function, the foundation moves. So if you call the absolute displacement z, we wrote the equation of motion in two forms. One was in this form, which was mu double dot plus cu dot plus ku. If you write it in terms of this relative displacement of mass, that would be negative my double dot. So this is one form of writing the equation of motion. So if the input is given in form of the acceleration data, that's the form you use. Or if you're interested in the absolute value or of the displacement, okay, this is what you have. So these two forms of equations of motion, depends of course on which case you are dealing with, represent the fact that the motion of the system can be in fact initiated as a result of an input displacement or the motion imposed on the foundation. And since we haven't studied a case of general forcing function, that this displacement can be of any form, which is the case in general. For the time being, if we assume that this input displacement is harmonic, then obviously the solution comes down to the case of harmonically excited systems. So in order to present at least one or two examples, I started with this example, right? We assume you're traveling on a road which is cyclic. In other words, the road roughness can be assumed to be of harmonic shape. And the length of each period, if it's L, and if the amplitude of this road roughness is Y, and this is sinusoidal, then if this is X, Y, which represent this function, would be sine of 2 pi x over L. Okay. Now, let's assume you have a car. Your car, to make a case simple, is traveling, okay, and there is no damping, so assume that this is an undamped system. And if it is moving with a constant velocity, we want to find the most unfavorable or undesirable velocity of your car under these circumstances. So given that the input we know is harmonic, given that we know the system is undamped, right? So what would be the most unfavorable speed? So I'm sure, exactly, you would immediately, at least intuitively, you would say, obviously, when the forcing frequency and the natural frequency of the system will be the same. So let's find out what is the forcing frequency. We say this is harmonic, but there's no time involved here. But we know that x, that this guy, the car is traveling with a constant velocity is this, right? So the input function, or the Rhodes function, would be what? 2 pi v t over L. So this is the frequency of the forcing function, which this input displacement represents. So what is the frequency of the system, or the natural frequency? Is the stiffness of that car over the mass of the car. The stiffness being the tire, the shock absorption system, whatnot. Or if, let's say, you have the weight of the car, you can write it as in this form. So the most undesirable speed would be what? When this frequency, okay, is equal to this natural frequency. Or you can find a desirable, undesirable speed, which is a speed in that case, that would be what? L over 2 pi square root of k g w. Although this may be seemingly an unrealistic case, you never have such a road, except maybe in an amusement park, that they actually make roads like this, which would be actually fun, because then you know how to exactly calculate the most unfavorable speed. If you go next time to Disney World or whatever, right? If they have such a thing, right? First thing you ask is, what is the weight of this vehicle that I'm gonna sit in there? Of course, don't forget to include your own weight as well, right? And, you know, then you have to guess the stiffness. You have taken the vibration course, so you can make, you know, evaluate that, right? Then, this is it, you avoid that speed. Otherwise, you get so dizzy and start, who knows, throwing up or something, yes.
What if you calculate the natural frequency of a chewed up hot dog moving around in your stomach?
Oh, that's really advanced.
And then make the roller coaster that same?
Sure, yeah, oh, that you're getting now to multi-geometry system, that's coming. Oh, but seriously, of course, this is a very, just sort of a rough assumption, but nevertheless, gives you an idea. You want to definitely, should you drive slower than this or much faster than that? Either case would work out. But what's the problem with going really much faster than this?
Oh, like the secondary frequencies or something, isn't there?
No, anybody? If you go much faster than that, what happens?
It'll be like that Reddit post where that guy had to shock you, man.
No, the state trooper is gonna catch you. That's the problem. Because you're gonna exceed the speed limit. That's the problem, right? So you may wanna go slower to be on the safe side. Or if you go faster, you know, tell the officer that I told you so, right? Okay. But anyway,
Throw it, not as hard.
so let's do another, little bit more realistic problem.
The yak of the shit.
Just in case.
Twice a
So let's do another problem, a little bit more realistic, I hope. Okay, let's say you have, this is another example. Let's say you have a system like this. So this is connected to a damper. So you have a support here, but this support is subjected to some imposed displacement. Again, since we have not studied the general case of forcing functions, let's suppose that this input displacement is harmonic. Okay? We'll make the case really easy. So let's say C2 is equal to 2, okay? And omega is equal to 1. This mass is 1, K is 1. So I know it's meaningless, but you know, these are some non-dimensional values or whatever. Right. So let's write the equation of motion for this imposed input displacement on this system. If this is moving u of t, okay, so the free body diagram would look like this. These two would be subjected to that displacement. So here you have k, u. This would be c1, u1, u dot. But this will be experiencing a displacement which is the difference of y and u. So this would be c2 times y dot minus u dot, right? Of course, assuming that u is larger than y, right? So the lumbar force would be this, right? So the equation of motion then would be m u double dot plus c1 u dot plus k u, right, minus, okay, c2 y dot minus u dot is equal to 0. So rearrange this, you get mu double dot plus c1 plus c2 u dot plus k u is equal to c2 y dot. C2 is given as 2. This is y, obviously this is 1. So you get what? You get 0.2 cosine of t. Okay? So that's the equation of motion. So this is F0, right? This, I don't have F1. Oh, the damping in the system. This damping is given as 0.2. I think it was 0.2 that was given. As 0.2%, 20% and 2%. Yeah, let me double check. The damping was given as 0.2 or 20%. So since I don't have C1, but I have damping ratio, I'm going to rewrite this in the other alternative form. So you have 2 zeta omega n u dot plus omega n squared u is equal to f0 over m, okay, cosine of t. Okay, so you want to find the maximum displacement that this mass would experience. That is the question that the problem is asking. How do you find the maximum displacement? You have a harmonically excited system, right? So U max would be what? Would be F0 over K, right? Times H of R. So F0 is 0.2. What is your K? Is given as 1, right? Divided by 1 minus R squared. R is going to be also 1 because it's omega over omega n, right? Omega n and omega are both 1. K and m are 1, omega n is 1, omega is 1. So at 1 minus R squared, right? So this term cancels out because R is equal to 1 plus 2 zeta, which is 0.2, times R, which is 1, okay? Squared, square root of that. So if you solve this, you get 0.5. Okay. So that's the maximum displacement this system is going to experience under that input displacement. Okay. So these are two simple problems, but the idea was just to show the application of this concept. We are going to get to more important stuff. Okay. Any questions? So what, as I said, what we have discussed so far has been really the effect of a forcing function or a force on a system or a displacement or input displacement on a system, right? So what we have so far discussed is basically if you have something like this, right? Which is the model of any mechanical or structural system, okay? If you had a force acting on the system, we know what happens to this. We know what kind of displacement this is going to experience, dynamic displacement this is going to experience, what kind of dynamic stress this will be subjected to, and so on, right? And of course, the case of input displacement, if this input obviously is harmonic, we have at least some feelings what happens, right? But what is really more important in vibration is not just evaluating what happens to the maximum displacement or the maximum stress in the system. The question is, if a force, dynamic force like this acts on this system, right? This system that we modeled like this consists of two main parts. One is this mass, and this mass is supported by these two, elements, which describe basically the support system of the structure, right? If you have a rotating machinery, this is the shaft, right? These are the bearings, and this is the disc, right? So the ultimate goal is that you want to make sure that this valuable system, which is the mass, which is a rotating system, would be safe. Or in other words, you really want to make sure that the force that these supports are subjected to, okay, is reduced as much as possible, because you really want to save your support system. What do we mean by the force that is generated in this support? See, this system, let's consider this case first. We look at the input displacement as well. Let's look at this case first, right? If this system is vibrating, this support will be subjected to a force, I call that F sub t, and I will define what it is. That would be what? In other words, the spring element would experience a force, which would be this, and a damping element, this. So this is the total force that as a result of this applied force is transmitted to the system, to the foundation of this system. We call this transmitted force. Okay? The force that acts on the system, for the time being, we have only looked at, of course, this as being a harmonic force. Okay? This is the applied force. One of the key objectives of vibration is that we want to reduce the effect of this force in generating this transmitted force. Or in other words, we want to make sure, okay, that the ratio of the maximum force transmitted to the maximum force applied is as small as possible, right? You want to reduce this. We call this transmissibility ratio. That's the goal. This is the concept behind what we call vibration isolation. That means if you have a system, vibratory system, like a jet engine, again, I'm going back into my example of a jet engine supported by this structure, the wing has a stiffness, has damping, right? You want to make sure the effect of the force, right? Harmonic force that is generated is really minimized on the support, or you're isolating the effect of that force. So this is the concept of vibration isolation. So how do we do this? How do we determine this? Again, so far we have only looked at harmonically excited systems, right? So let's see how we can evaluate then that ratio and study that, okay? So what is that ratio? So in the case that you have the input force is this, right? Obviously, the maximum F of t, max, is what? Is the amplitude of this harmonic force, right? But what is that transmitted force? The transmitted force, we said, is K times U plus C U dot. In the case of harmonically excited system, what was U in general? U of t was what? Was F0 over K times H sine of omega t minus theta. You remember the solution to the damped oscillation under harmonic law, right? So if this is U, therefore that transmitted force would be what? Would be K times this, so it would be F0 H sine of omega t minus theta, right? So this is what? This is k u, right? Plus c times the derivative of this, right? If you take the derivative, you see that this would be what? F0 bar h divided by k. So that part, that omega, cosine of omega t minus theta, right? So this is C u dot, okay? But by now, so we want to find the maximum value of this force, right? What is the maximum value of this force? This is a sum of two harmonic functions, right? So by now we know, what is this? If this is alpha, right? This is beta, right? So this transmitted force that you have is of this form, right? Alpha sine of omega t minus theta plus beta cosine omega t minus theta. By now we know that you can write this as a single harmonic function, right? And that would be what? Would be of like this. Alpha squared plus beta squared. You do this, alpha divided by this, sine plus beta divided by this, cosine, and you know that this is sine of some function, whatever, phi, and this is cosine of some function, phi, so some of these two become what? Say, sine of phi plus whatever, right? So, but we don't care about this part. All we are really interested is the maximum value of this. Maximum value of this means what? The amplitude of this harmonic function, right? So, in other words, the maximum force transmitted is what? Is this alpha squared plus beta squared. And what is that alpha squared plus beta squared? This is alpha, this is beta. So if I square those and add them up, this F0H is common. So F0H comes out of that integral, and you get 1 plus c squared omega squared over k squared. Okay? So this is the maximum force transmitted, and we want to find the maximum, maximum force input. We want to find the maximum force transmitted, right? So if you substitute for, of course, h is what? H is 1 over 1 minus r squared plus 2 zeta r squared, right? So we have that, okay? So let's look at this other term. But what is c squared omega squared over k squared? Like before, I'm going to do this. I'm going to multiply this by 4 omega n squared divided by 4 omega n squared. Okay? Again, look at this. This is r squared, right? Except r squared times what? I keep actually this 4 here, so it would be 4r squared times c squared. Omega squared is what? K over m divided by k squared. So this would be what? Would be, well, I keep this 4 here, right? So you have c squared over 4km. okay? You remember that zeta was what? Was C over 2Km. That was definition of damping ratio. So what is this then? That would be what? That is zeta squared, right? So, yes?
Where did that R squared go in the,
This R squared is omega, is right here, right?
right,
Ratio omega squared over omega n squared.
and then in the next step it like,
I replace omega n squared by K over M.
On the right side of the equal sign, you
So-
don't have the 4 times r squared.
I have, yeah, well, this is times R squared, yeah, I was just
oh,
looking at this
What
point.
about the 4 in front of the r squared?
That is 4 also.
Okay.
Right.
Isn't the 4 cancel out?
No, I don't want to cancel it out intentionally.
Oh.
I keep it there because I separate those two, because this part becomes zeta squared. So it becomes zeta squared, this whole thing then becomes 4 times zeta squared R squared. That's why I kept it, right? So, as you can see now, this 1 plus C squared omega squared over K squared then becomes the square root of 1 plus 4 zeta squared R squared. Okay? So now, if you divide this maximum Ft, which is what? F0, right? And I would write that H, okay? 1 minus R squared, plus 2 zeta R squared, times 1 plus 4 zeta squared R squared. Divide that by maximum input force, which is just F0. These two cancel out, therefore transmissibility ratio becomes this. 1 plus 4 zeta squared R squared divided by 1 minus R squared plus 2 zeta R squared. So this function represents the ratio of the maximum force transmitted to the foundation and the maximum force that is acting on the system. Very interestingly, if you plot this now, and let me do that, I'm going to use a different color here. Take advantage of all the luxury we have here. Okay. Oops. I made a mess here. Okay. Okay. All right. Forget about that. So, if you plot this, I think you don't need this. You see something very interesting happening here now. Okay. So, if you plot this function, again, I don't want to go through all the mathematics of it, and you can do that, of course, for yourself and so on, but let's assume that you know how to plot these functions. This is what you see. Okay. If I plot, obviously, what we are interested is the case that damping ratio is less than 0.707, right? Because who cares if you have damping ratio more than 707? Why? Because you know that dynamic response always less than the static response, so you don't have to worry about the adverse effect of dynamic motion, right? It is here that we are interested. If you plot these, this is what you see. Okay? That all of these curves, intersect as R is equal to the square root of 2. And then something else that you also notice is that as the damping ratio is increasing, let's say 0.1, zeta 0.3, zeta 0.5, and so on, okay, which let me actually label those here also. This is zeta 0.5, let's say this is zeta 0.3, let's say this is zeta 0.1. You observe, you know, if you really read this or study this curve carefully, there are a number of observations you can make. So let me actually summarize them and write them down, okay? You don't need this anymore, we plotted it, okay? First of all, observation number 1. In order to reduce the effect or the adverse effect of that forcing function on the foundation, or reduce their transmissibility ratio, right, R should be greater than square root 2. Or in other words, omega should be greater than, okay, square root 2 omega n. Okay, that's the first observation you make. Okay? What does that mean? That means the larger the value of R is, right? Obviously for a given, well, let me write it down. For a given zeta, let's say for this one, for a given zeta, the larger the value of R is, right, the smaller the transmissibility ratio is. So as for a given zeta, as say R increases, transmissibility ratio decreases, right? Okay, so obviously R is, as I said, omega over omega n, right? So in order to increase this, if this is constant, in order to increase this, you have to reduce this, right? So in order to have the lowest transmissibility ratio possible, you want to have a very, very small omega n. What is omega n? Omega n is k over m, right? The mass of the system is, give or take, is always constant, right? So that means you need to reduce k, right? So that means an effective vibration isolation is when the stiffness of the support system is as small as possible. In other words, the system is as soft as possible, okay? If you make, for instance, the bumper of a car from chewing gum, right? It would be the most effective vibration isolator. But what happens? Smaller stiffness means larger displacement. So that's not good, right? Otherwise, you would put all these systems on a jumpy, what is it called? They call it just a piece of string or something, very, very soft, right? So that's, in other words, you have to make some kind of a compromise here. Observation number 2, look at these. You remember in the case of the general harmonic force, we said that, okay, the higher the damping ratio is, what happened? The larger the damping ratio is, the further you reduce down the displacement, right? Look at here. The more you increase damping ratio, right? In fact, transmissibility ratio is increased, right? So that damping is increased for a given R, right? In other words, if for a given R, this was for a given zeta, this is for a given R. For any particular value of R, right? You see here, the higher the damping, the higher the transmissibility ratio. So your best isolation system is a combination of a relatively soft stiffness and a very low damped system. Okay? That's sort of the optimized solution. Okay? And obviously, of course, we're not talking about zeta greater than 0.707 because you know that dynamic response is always less than the static response. We don't care about that. This is for the case that you have a system with a damping ratio less than 0.707. Okay? So, again, compare this, of course, with the frequency response function for a damped system. You see that this is quite different. So these are the most important, really, sort of conclusions that we draw. That you, in terms of designing a system that really isolates the adverse effect of a forcing function, you want to have a good combination of a low damped and relatively moderate stiffness. And there are many, of course, vibration isolation systems made that way. Interestingly enough, as we will see, that if you now study the second case, which is the input displacement, okay? Input displacement. You see that the transmissibility ratio, which is defined as the maximum displacement, okay, or the maximum, okay, maximum displacement experienced to the maximum input displacement, which in this case is the definition of transmissibility ratio. Interestingly enough, the equation for that comes out to be exactly the same for the case of harmonic, of course, input displacement. So for the case of even isolation, when you have an input displacement, earthquake, right? You want to have soft stiffness, low down. That's the reason actually for a structural system it's easier to, in fact, describe that. If you look at almost every single building in the world, if you want to design them to be better earthquake proof, you make sure that the first floor columns are very soft, because if they fail, the whole structure becomes intact. Or you put vibration isolators like rubber or things like that underneath the building that are very, very soft, that actually, when the earthquake comes, they can move a lot, but basically absorb a lot of energy. So that's, we're going to continue on this concept of vibration isolator next time. So